All right, round 2 of graphing rational functions. So remember, a rational function, like the reciprocal function that we looked at in the first video, was we had the parent function and then we had some basic transformations to it. Now we're going to look at more complicated rational functions, and so the steps are a little bit different. It's a little bit harder than just finding the transformations. So what you're going to have to do is you're going to have to simplify the function. So remember, it's a fraction, so you might have to factor and cross factors out and that sort of thing. And then using what you've just done, the whole simplifying process, you're going to identify any holes in the function. Okay, you're going to identify any holes in the function. Well, a hole occurs if one of the factors crosses out. So if you're simplifying and one of the factors crosses out, you're going to have a hole. Now, hole is literally just an open circle or open point on the graph, but you have to know where that point is. So to find the x coordinate for that hole, all right, you're going to set the factor, or factors, because I guess you could have more than one hole, set the factor that crosses out equal to 0 and solve for x. Okay, and once you have the x coordinate, all right, because again, this is going to be a point, you need the y coordinate. So once you have the x coordinate, you are going to plug, right, the x value that you just got you're going to plug that into the simplified function. Okay, so the function you got when you simplified earlier. Okay, so it's important that you plug that into the simplified function. All right, so you'll get practice with that in just a few minutes. Again, we're just taking notes. All right, so what are the other steps? Well, you still have to find vertical and horizontal asymptotes, but it's a little different than it was before. Okay, so to find the vertical asymptote, all right, it might be more than one, by the way, you're going to, all right, so you're going to find it by setting the simplified denominator equal to 0 and solving for x. All right, so there's a little bit of solving involved. For horizontal asymptotes, there are actually some rules that you have to know and pay attention to. Okay? Now, keep in mind, right, we're talking about a rational function. We're called the top, when we're being generic, p of x, and the bottom, q of x. So when you look at these rules, and it says the degree of p is less than the degree of q, I'm just talking about p being the top and q being the bottom. Okay, and we've actually talked about the word degree before. Degree is just the highest power of x, highest power of x. So you have to figure out what is the degree of the top polynomial, what is the degree of the bottom polynomial, and then compare them. If the top degree is less than the bottom degree, your horizontal asymptote is automatically at y equals 0. But if the degree of the top is equal to the degree of the bottom, okay, then you have to do a little bit more work. You're still going to have a horizontal asymptote, and by the way, you can only ever have one of these. So you're still going to have one, but you find it by taking the leading coefficient on top and dividing it by the leading coefficient on the bottom. All right, the coefficient is just the number in front of the highest power of x. All right, and then last but not least, if the degree of the top is bigger than the degree of the bottom, I guess I should change colors again. If the degree of the top is bigger than the degree of the bottom, we do not have a horizontal asymptote. Okay, so you actually do need to learn those rules. And then once you have all of that information, you can use Desmos to find the x and y intercepts so that you can make a more accurate sketch. And then once you have your sketch, you're also going to have to tell me the domain and range. And then we're going to go back and look at end behavior. So we're bringing back something we've done in the past, and we're going to look at intervals of increasing and decreasing. All right, so the problem I have for you here, number 5, is actually the same type of problem we've already done. Okay, so because the top is a constant, and the bottom is just x plus or minus a number. But I don't want to do it the old way. I'm not worried about the transformations right now. I just want to work it with the steps we just went over. So the first step is to simplify the function if I can. That means, can I factor this and cross anything out? No, I cannot. All right, so if I can't simplify it, that means nothing crosses out. So if nothing crosses out, there are no holes. So you just put none right there. Okay? There are no holes because nothing crosses out when I factor, because I can't factor. All right, for my vertical asymptote, the rule says set the bottom factor or factors, if there's more than one, equal to 0 and solve for x. And that is my vertical asymptote. And just like it was before, if that's my vertical asymptote, then my domain is automatically x cannot equal that number. All right, but for my horizontal asymptote, I have to figure out what is the top degree, what is the bottom degree, and compare them. All right, well, the degree is the highest power of x. If there is no x, that degree is 0. If there is an x, the degree is its exponent, which in visible exponents are 1s. Well, how does 0 compare to 1? It's less. So then we have to remember what rule, what's the asymptote when the top degree is less than the bottom degree. So look back at your notes. Top degree less than bottom degree, y equals 0. And if the horizontal asymptote is at y equals 0, then the range is y cannot equal 0. And that's really all the math that you have to do, okay? The rest of it is graphing using Desmos to get your x-intercept and your y-intercept, excuse me, and then plotting your points. Okay, so I'm sorry about that yawn. All right, so I'm going to go over here to Desmos. I don't need that. I need a -2 on top and an x plus 1 on the bottom. Okay, so you can see that you actually have a y-intercept, right? But you don't see an x-intercept, and if you zoom out a little bit, you still aren't going to see a gray point because you don't actually touch the x-axis. That's because it's an asymptote. All right, so what was my point again? 0, -2. So my y-intercept is at 0, -2, but I don't have an x-intercept. And that makes sense because I have a horizontal asymptote on the x-axis, so I shouldn't touch it. I have a vertical through x equals -1. Okay, and then let's see, I had a y-intercept at 0, -2. And my graph has to go through that intercept, has to come along the asymptote, and then go up and along this asymptote. Try not to make it look like it's going to curve down. And so that was one of them. And then if you look back at Desmos, the other one was over here. Okay. All right. So there's my graph. Now, end behavior. End behavior. All right. So look at what I have written here. I've already filled in what ends I want you to look at. It says as x approaches -infinity. Remember, that means the left. That's over here. Okay? And then the second one says as x approaches +infinity. That's the right. That means I want you to look over here. Okay? So I want you to tell me what y value these ends are headed towards. Okay? Well, maybe you need Desmos to help you. But the whole idea that you have to understand is that these will never curve. These will never start going up or down, all right, no matter how far out you look, all right? So that's really bad. All right, it will never turn, okay? So this end will stay flat along the asymptote, and the right end will also stay flat along the asymptote. And we're looking for a y value, so it makes sense that it matches the horizontal asymptote of y equals 0. Okay, so this asymptote is going to tell you your end behavior. And that's always going to be the case. The asymptote is going to tell you the horizontal asymptote is going to tell you the end behavior. Now, for increasing and decreasing, you have to remember that those are intervals of x values, okay? So your domain is going to help you know when to stop increasing or decreasing, okay? It's going to tell you, so if you look at your domain, it's going to tell us to stop at -1, but we do have to trace our graph from left to right, right? X values from left to right, okay? So I'm going to start on the left. Let me get a different color so you can actually see what I'm doing. I'm starting here and I'm tracing my graph. And it kind of starts out flat, but then it starts increasing. And this one's actually going to increase forever. But I'm talking about the x value. And remember, it never crosses this asymptote. Okay? And that asymptote is at -1. So I increase from -infinity to -1 because I'm doing x values. All right? Well, then I have to stop that interval, break, and I'm going to start a new interval. Okay? So then I go to my second curve and I start as far left as I possibly can and I trace. Again, that one's actually increasing as well until we reach our asymptote. But remember, we're going to the right, and the right is +infinity. So we're actually starting at -1 again, and we're going to the right forever. So notice All right, my domain is all the x's except for -1, and so is my interval. All right, it's just interval notation. I know that's, you might have to listen to that again just to let it sink in. All right, but just understand that, and you could think of it as stopping at the asymptote. Okay, your interval has to stop at any vertical asymptote and then start again on the other side of that vertical asymptote. And that's technically what we've done here. And the reason that these are not squared off brackets, okay, is because we can't actually equal -1. We never actually touch it. So these need to be parentheses. So if I was increasing for both curves, then just remember you need to put decreasing here. Okay? All right, I'm actually going to stop this video here and then do the rest of the examples in a separate video.